Hello, this is Dr. Behrang Askarian. I am an associate professor at Washington State University, the Mechanical Engineering Department. I am also a licensed professional engineer in the state of Washington, a PE, and my area of expertise is thermal fluids. Make sure you subscribe to this channel because I try to, upload one video a day in the area of heat transfer, fluid mechanics, and thermodynamics. This video is about piping network. It's about the problem that normally you can't solve by hand. So we have two parallel pipes and we have to calculate, and we have the pumping power is given and the pump efficiency is given, and we have to calculate the flow in each branch. And these two branches are actually in parallel. So that's what the problem is. And since we don't know the friction factor in any of these branches, you have to actually calculate friction factor. You have to apply mass conservation, all these laws at the same time. And when you apply them, you realize that you can't solve this by regular, methods. You have to solve it numerically by iteration. So this problem is example 8-8 from Cengel's fluid mechanics book, 4th edition. So let's take a look at it. All right, here's a problem that we are looking at. This is example 8-8. So what you have here, you have two reservoirs. You have reservoir A and then you have reservoir B. They have different elevations in terms of like the free surface of water is at 5 meters here, and for this one is at 13 meters. We have two branches of pipes. First, we have a pump here. This one is the pump. The total mass flow rate, in fact, goes through mass flow rate total, if you want to call it mass flow rate total, goes through the pipe right before the pump. And then here we have two branches. It goes to branch 1 and goes to branch 2. So in branch 1, we have m.1, and in branch 2, we have m.2. And eventually, they become the total mass flow rate again, whatever it was at the beginning, and goes to the second reservoir. That's the idea. So some information about the pump is given. For example, the amount of electric power that goes into this pump is given, the efficiency of the pump is given, and the diameter and the length of these two branches are given. Both of them happen to be like 36 meters, and the diameters are given. And the pipe material is also given, as it's made of commercial steel, which means that if you go to the Moody chart, epsilon for this case is 0.045 millimeters. So that's the information that you need to have when you want to calculate the friction factor. The total amount of W dot electric is given as 8 kilowatts, and pump efficiency is given as 70%. The water temperature is at 20 degrees Celsius. So we have pretty much all the information. Once you have water temperature at 20 degrees Celsius, you can find the density, you can find the viscosity of it. You need these things for, Reynolds number eventually. And the diameter of the pipes are given in terms of centimeter, by the way. And of course, ZA and ZB is given. So all the information is given. If you want, you can pause the video right now and read the problem and make sure that you got all the, all the information about this problem, and then you can write them down. And then now we're going to move to EES to solve this problem. Before moving to EES and solving this problem, you got to keep in mind that we need to have some sort of game plan. That's what I call it, a game plan. A game plan is you need to have a set of equations before you start writing these equations in EES. You need to know where you're going with this. Basically, if you don't know what you're doing, you can spend a lot of time just debugging a code that is not going anywhere, basically. So before we do that, we need to actually sit down and write down all the equations that are going to help us. And then we're going to move on to EES and solve the problem. So let's move on to a different page and just organize our thoughts. Let's just write down all the equations, because in EES, I need the same number of equations and unknowns. And let's do it. Okay, so this is the problem. We want to see what our goal is. Our goal is eventually to calculate what would be the velocity in every single branch. So what would be V1 here? I'm looking for this one, and V2 here. So I can find eventually what would be the mass flow rate in every single branch. That's the ideal goal that we're looking for. And the information that is given that this pump is consuming about, W electric watt, it takes about like 8 kilowatts, and the pump efficiency is about 70%. This is the information that's given, plus the length of the pump, commercial steel. We talked about that. Epsilon is 0.05 millimeters for commercial steel. That's what it is. ZA, ZB is given, and the diameter of the pipe and everything else is pretty much given. And the temperature of water is also given as 20 degrees Celsius. So you can find the density and viscosity of it. That's pretty much it. That's our goal. With all the information that is given, and it also, the problem said that, ignore the minor losses. So the only major loss that we're dealing with is because of the pipe length. So L1 and L2, both of them are given the same number. In fact, 36 meters. Now, when you want to when you look at a problem like this, you're like, okay, how many equations do I have? Let's just write all the equations that I have so I can enough equations and enough unknowns. This is the process that we're going through when you want to solve it numerically by iteration. You need to have enough equations and enough unknowns. So let's just make a list of all the equations that are going to work for us. The first equation that comes to mind is basically the energy equation, or modified Bernoulli equation. If I write the energy equation between point 1 and point B, point A and point B, because the velocity at this point, so I'm going to write it between this point and this point. So the pressure between point B and point A is the same. And of course, the velocity at point A and point B is the same and is 0, like this. So when you write the energy equation basically simplifies. So this is going to be your first equation. Your first equation simplifies as ZA. And then from ZA, you have to look at, where are we going? We're going through the pump here, and then eventually we go from here to, it goes through the pump through both branches and it comes out. So ZA plus pump head in this case equals ZB plus all the head loss from point 1 to point A to point B. That's the first equation. So right now I have two unknowns in this equation. In fact, this is an unknown, HP is an unknown value, and HL is also unknown. And you might say, okay, HP is known. No, it's not, because I don't know the total M dot. The total M dot that goes, this is the total M dot that goes through the pump first, and then gets distributed into M dot 1 and M dot 2 in these two branches. I actually don't know what that value is, because if I knew, I could, find a way to, using mass conservation or something, I could find it. So that's the first equation that has two unknowns. This is not going to be helpful. So what you do is basically you go through all these unknowns and you find equations that could help you with the unknowns. We can start with, HP. So what equation has HP when, fluid mechanics? The fluid mechanics equation, the second equation gives you this, that, if you multiply the efficiency of the pump by W dot E, the electric power, that equals M dot total. M dot total is the total that goes through the pump times G, we know what it is, times HP. Okay, I did that. If you look at the left-hand side of this new equation, everything is known, except on the right-hand side, I added one more unknown here. And the new unknown that I added here, I'm going to show it with a different color so you can distinguish all these, is this guy, is the M dot total. So just to be consistent, I'm going to show the other guys with also red so we know what's going on. All right, so I added one more equation, but also I added one more unknown. So that's not going to help us. I need same number of equations and unknowns. So I have two equations, and in fact, I have three unknowns. I have HL, HP, and M dot T. I don't have it. Okay, let's add another equation that can help us with M dot T. Another equation that can help us is M dot T mass conservation. M dot total would be basically the combination of M dot 1 plus M dot 2. Okay, this equation is not going to be that helpful because right now I added one more equation, but I added two more unknowns to the system of equations. So I need to define M dot 1 and M dot 2. Okay, let's see what equation I can use to find M dot 1 and M dot 2. Equation 4 in this case would be M dot 1 equals rho. Rho I can find because I have the temperature of water and I know it's liquid water, so I can find rho. That's not a problem. Rho times V1 that I don't have, times A1, the cross-sectional area that I need to calculate somehow. So that is another unknown. And, A1, I can calculate it. That's not like an unknown thing because I have the diameters. But V1, I actually don't know. So I added, again, one more unknown to this whole process. That is still not helpful. Equation 5 is the same, is the equivalent of equation 4, basically. M dot 2 is rho times V2 times A2. That would be equation 5. Okay, so what else did I have here? I kind of did a lot of these things. So V1 and V2 showed up as a couple of new unknowns. All right, so what would be the next plan? I have to write equations that have V1 and V2 somehow in them. So, I can add more equations. Eventually, I get the same number of equations and unknowns. All right, let's take a look at this guy. This guy here that we didn't talk about much, head loss. From point 1 to point 2, there is one very important fact that we have to take into account. That these are two parallel branches. If you go back to fluid mechanics, for two parallel branches, head loss is the same value. That's one of the magics in fluid mechanics, that when the process becomes steady state, once we reach steady state, the laws of fluid dynamics will adjust the flow rate such that the amount of head loss in every branch that is parallel to each other becomes the same. So there's only one head loss from point 1 to point 2, which is the same head loss that showed up between point A and point B, right? And that head loss is the same in every branch. So that can give me two more equations. These two equations would be these guys. Head loss is the same head loss as head loss 1, basically. It's the same. Head loss 1 is the same. You can't write it like this in your EES code, but we'll fix that. So head loss is head loss 1, which is F1 that I don't know again. L1 I know, D1 I know, V1 that I was looking for that just showed up, 2G. And same logic, that head loss equals also head loss 2 equals F2 times L2 over, let's write it this way, L2 over D2, V2 squared over 2G. Now, question, how many unknowns did I add again? I added to V1, I added two equations that include V1 and V2 that were formerly unknown, but I added two more unknown values. And head loss 1 and head loss 2 are the same, so I don't have to worry about it because I am showing it here and here that these guys are the same. So I added more. Now I need to add equations that can take care of friction factor. So the equation that takes care of friction factor is the Kohlberg equation, the equivalent of the Moody chart, right? So let's write it. So this would be equation 6. This would be equation 7. Let's write equation 8. Equation 8 would be, okay, that would be 1 over square root of F1, which is the Kohlberg equation I'm writing for you, square root of F1 equals -2 times log 10 of epsilon over D1 over 3.7 plus 2.51 over the square root of Reynolds 1, because Reynolds in every branch is going to be different. Not the square root of Reynolds, I'm sorry. Just Reynolds 1 times the square root of F1. And if you check the Kohlberg equation, you'll see that this is the Kohlberg equation from the Moody chart, basically. Okay, now the equivalent of this would be equation 9, basically. So that would be equation 9. Equation 9 is 1 over square root of F2 equals -2, number 2, basically, log 10 times epsilon over D2. Let me see if I can write it nicely. Epsilon over D2 over 3.7, just the number 23.7, over 2.50 plus 2.51 times Reynolds number 2 square root of F2. That would be another equation. So I added two more equations, but in this process, I added two more unknowns. And these two unknowns are Reynolds numbers. So I added this Reynolds number here, and I added this Reynolds number here. So I need to add an equation that takes care of the Reynolds number that I don't have. Let's write equations. 9, 10. Equation 10 would be Reynolds in first branch is basically rho times V1 times D1 over mu, and Reynolds 2 is basically rho times V2 times D2 over mu, like this. So that's equation 11. If you take a look at this, assuming that you know the values of A1 and A2, and you kind of know because eventually you are going to find the values of an A1 and A2 as pi times D1 squared over 4 and A2 as pi times D2 squared over 4. You can, find these values like this. Assuming the fact, let's just count the number of our equations and our unknowns. If you have enough the number of equations and unknowns, we can probably solve this problem. Because the last two equations, Reynolds numbers, did not add any new unknowns. So I have 11 equations, and I'm looking for the number of unknowns. The number of unknowns, I'm going to just show it with a different color here, so it can, keep track of that. These question marks, red questions are the unknown values. That's number 1, number 2, number 3, 4, 5, 6, 7, 8, 9, like this, 10, and 11. And I do have 11 equations. So I have 11 unknowns. If I want to make a list of my unknowns, the unknowns apparently are the value of HP, that's the unknown. Value of head loss is the unknown. Head loss 1 equals head loss 2, doesn't matter. So m dot total, right? M dot 1, m dot 2, these are unknowns. Then V1 and V2. And for V1 and V2, we have F1 and F2. And of course, for F1 and F2, we have Reynolds number 1 and Reynolds number 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 11 equations. Now I have enough equations and enough unknowns. You can solve this problem in ease. However, there is some trick to it. Because if you look at this guy, if you look at friction factor is an interesting equation, the Kohlberg equation. You can probably use the other equation, the Holland equation that we have in the book. But, Kohlberg equation is the Moody chart, basically. First of all, you might ask this question, how do you know this is going to be turbulent? I would say this is turbulent. You're dealing with an 8 kilowatt pump. And these diameters and water, from experience, it's turbulent. Also, it says commercial steel. If it is commercial steel, I know this is going to be turbulent. So I directly went for the Kohlberg equation. I didn't need to write like 64 over Reynolds number or anything like that. This is not a smooth pipe, and this is definitely not going to be laminar. If there is a problem that's going to be laminar and you solve it and you calculate Reynolds number at the end, Reynolds number turns out to be like less than 2300 somehow, and it is a smooth pipe, then you have to revise your solution and then go back and resolve it with the assumption that the friction factor, you're going to use a laminar equation for friction factor, which is 64 over Reynolds number for circular pipes, circular smooth pipes. This is not the case. So there's another trick that we're going to encounter when you write the code that, you can see that, the Kohlberg equation is an implicit equation, 1 over square root of f on one side. And then on the other side, you have a square root of f inside a logarithm. That is an implicit equation. Not only that, f is a square root. So when EES is iterating, it needs to iterate in the positive range of numbers. If it iterates in negative range, it's going to send you an error message. And that's what's going to happen. You're going to see it. And there's a trick to it that we can, do this trick and, force EES to iterate in the same range, in the good range. So you can, so the code can, converge faster and get you the answer. We're going to get there. But in terms of the number of equations unknowns, we're solid. We're solid. So now we have our game plan. And based on this, we can move on to EES and start writing the code and solving the problem. I suggest that if you have your notes in front of you, open EES and just like the way I'm writing the code and I'm testing it and I'm the testing solution, you actually go ahead and do the exact same thing, with me. And then at the end of it, you're going to get the same number if you have not made any mistakes. Hopefully, I'm not going to make any mistakes in this problem. So let's go to EES. Now is the time to write a solid EES code and solve the problem beautifully. All right, here we are in EES, and we're going to start writing our code. So the first thing that, you can add your name at the beginning of your code. Doesn't matter that much, but anyways. So let's start with the given values. But before I do that, I have to go. Oh, well, by the way, if you don't know how to use EES, I put a link in the description where I showed how you can use EES. So go back and watch that video first and then come back here and everything will make sense to you. If you already know how EES works, then you know how EES works. So that's not a problem. First, the first step in EES is you got to go to the unit system. You got to go to the unit system and pick the right unit system. Since we have velocity in meters per second and everything, and I would go for basic SI units, basically. So I have joules, so it means when I choose joules, I have to use watts instead of kilowatts and things like that. So I'm going to do basic SI units because I'm going to do W dot of pump is M dot GHP, things like that. HP is in meters. And M dot is kilograms per second. I have to do joules. I have to do basic SI units for this problem. The only thing so I'm going to Pascal here. The only thing I can get away with is Celsius because I'm not dealing with any ideal gas law, any entropy, any stuff that actually needs Kelvin. So I can just get away with Celsius and I'll be fine. But use basic SI units and just keep Celsius. Celsius is SI, but it's not basic, like basic SI is Kelvin, right? All right, okay. And now we're going to get started. So we're going to start with the given values. The given values are usually, the values that the problem gives us, like the diameters, like the temperature of water, like things like that, like epsilon. It says commercial steel, right? So let's get started with all of these very quickly. Epsilon equals 0.045 millimeters based on Moody chart. Convert, millimeters to meters like this. And I'm going to just write a note here because this is commercial steel. And if it is commercial steel, your question is, okay, where do I get that information? Go to Moody chart. Open the Moody chart or the tables in fluid mechanics book. They give you the value of epsilon for it. And then you have your answer right there. Just for you guys to see where I got the value of 0.045 millimeters for roughness, this is the Moody chart, right? If you go to the Moody chart, and this is the commercial steel, you can see is 0.045 millimeters for the value of roughness. Epsilon, this is where you can get the values of roughness if you need it, or the friction factors. However, in this case, we have to iterate to find the correction, to find the correct friction factor. So let's go back to EES and continue solving the problem. All right, we're back in EES. So commercial steel, we got that. Let's keep going. Temperature that is given is 20 Celsius. I'm going to need this for viscosity and density. What else is given? The efficiency of the pump is given as 70%. I'm going to add this here. What else is given? Temperature, whatever, ZA is given. ZA is supposed to be 5 meters. Again, if you didn't catch these, you can go to the beginning of the video, write down these values when I showed the slide and everything. You can pause it, and so you can have all the information. ZB was given as 13 meters, right? What else did we have? We had the values of L1 and L2. L1 was 36 meters, and apparently L2 was the same value of 36 meters. Both of them had the same value. Diameters were given as diameter 1 was 4 centimeters. So I have to convert it to basic SI units from centimeters to meters like this. And then diameter 2 was given as, from what I see, is 8 centimeters. So 8 centimeters times convert from centimeters to meters. So everything looks good, except that I messed up the parentheses. I just fixed it. It looks okay. Is there anything else I need to add? Yes, W dot of the pump was given also. W dot electric that goes into the pump was given as 8 kilowatts. So it's 8,000 watts. I have to do basic SI units because I told you why. You have M dot, you have HP. These are basic SI units. So because I have this, I have the basic given values. It's a very good idea to check the solution. See, everything is good. Everything is nice. And so I have no unit problems. Everything looks pretty nice. So I am good to go. Now, what's the next step? So let's go back and keep going. Okay. Now that I have this, I can, the code, I can start the solution to this problem. If I typed the word solution correctly, I did. There are things that we can calculate at the beginning of the code that we're going to need. And let's do that before we get to those 11, crazy equations, 11 equations, and 11 unknowns. First of all, I can calculate the values of, areas. So it's just say pi times d1 squared over 4, like this. And A2 also would be the value of pi times d2 squared over 4. So I got these values. I remember, I think I have to add one more thing here that's going to show up, and that's the gravity. G is 9.81 meters per second squared. Don't forget this one. You need G for the solution. Okay, cool. Now let's run it. Let's run it again. Okay, I got these two values. They're in meters squared. I have to fix the unit, meters squared. Okay, now I don't have any unit problems. Everything looks really nice and good. I like it. And let's keep going. There are a couple of other things I need to calculate or find: density and the viscosity of water at this particular temperature. So this is a technique I'm going to use. Rho density equals density of water, right? Water, I need two independent properties. T is the T that is given in the code, and I give it a quality of 0, which means liquid water for ease. So I can find the density correctly. And of course, I can find the viscosity of water. So you can go to the tables, or you can do it this way: viscosity of water, and I can just copy and paste Control C and Control V, the same thing. And I have density and viscosity of water, which is going to show up in Reynolds number. Let's run it. Let's see what we got. Okay, of course, I have to fix a couple of units here. Mu is, the unit of mu is Pascal second. Pascal in EES, when you show dash in the units, it's like multiplying the units. So Pascal dash second means Pascal's time second. Only in the units. Do not do that for the code, right? And density is kilograms per meters cubed. So it's kilograms slash M3. You don't need to show the chevron. So only in units, all right? Don't do this for the code. Now, you see how nicely everything is looking and no unit problems? Beautiful. Okay, you can save your code. Don't forget to save it. Let's keep going. Now we're getting to those simultaneous simultaneous equations. It's supposed to have like 11, 13, 11 simultaneous equations. Those equations that I wrote for you on when I had OneNote open, my notes open. So let's take a look at them one more time real quick. If I want to share that one more time for you, so you remember what I'm talking about. The simultaneous equations are these equations. Equations 1 to, look at this. From here, equations from 1 to equation 11, all these equations, we're going to use these ones. And hopefully you wrote them down in your notes and stuff. And so it's going to work out. So let's go back to EES and just type all these equations. That's how it's going to work. Okay, so the first equation that we're dealing with here was the energy equation, also known as the modified Bernoulli equation. Okay, ZA, if I remember correctly, plus HP, pump head, equals ZB plus head loss. Okay, that's one equation. It looks good. Second equation was eta P times W dot E equals M dot total times G times HP, like this. That would be the equation M dot GHP of, work of the pump, power of the pump that goes into the fluid is, if you multiply the, the efficiency of pump by the electric work, you give to the pump, right? It looks like that. All right, what was the third equation? Third equation said m dot total equals m dot 1 plus m dot 2, like this. Something that can help you, every 3 equation that you type, I'm sure up to this point in the code, everything is okay, because I just ran it. I ran it and checked the units and everything. So if there is any error that is going to happen, is going to be here. That's going to cause the error. So what I'm going to do here is every 3 lines that I write, I can't run it now because these are not enough equations, enough unknowns. If you do this, for example, you see you have 18 equations, 20 variables, it's not going to work out, right? So, but I do this. I go to the formatted equation to look at the way that the equations look, to check to see everything is typed correctly. And so far, everything looks okay. So MT, M dot T, M dot T, everything looks okay. So every 3 equations I write, I'm going to run it in the formatted equation, and I'm going to check to see if it looks good, right? That's the technique. All right, let's keep going. Now I have to add the equation 4 that we wrote. M dot 1 equals rho times V1 times A1. Luckily, thankfully, we calculate A1 and A2. And M dot 2 equals rho times V2 times A2. That's how you do this. Okay, and equation 6. Equation 6 was head loss, is the same in both branches, is F1 times L1 over D1 times V1 squared over 2 over G, like this. And also, this is another equation that connects, that closes all the equations. It's the fact that head loss in both branches is the same value. Equals F2 equals F2 times L2 over D2 times V2 squared over 2 over G. All right, so is this okay? Let's take a look at it in the formatted equation. Formatted equation, let's take a look at it. M dot 1 is rho V1 A1, rho V2 A2. Beautiful. H head loss. Head loss has to be the same. Has to be the same head loss that you had here. You see this? You see this? These two have to be the same variable. All right, F1, L1, D1, V1 squared 2G, V2 squared 2G. Beautiful. Looks good. Looks good. I like it. Let's keep going. Okay. Equation 8. That's the Kohlberg equation. All right, let's write 1 over skew RT of F1 equals -2 times log 10. Log 10 is the function it is. Log 10 of epsilon over D1 over 3.7 plus 2.51 over Reynolds over square root of F1, like this. Let's see if it looks okay. I'd like to take a look at it to see if this thing looks okay. Yeah, this is okay, but if you want to make it look exactly like whatever you had in Kohlberg equation, you can put these two in parentheses like this and just multiply these guys, and it's gonna look nice. You can do the same thing with like this one, epsilon over D, because you want this thing to look really nice. I don't know if that's gonna help anyways, but we'll see. So let's look at the equation this way. So it's going to look like this, 2.51, and it looks like it is fine. One thing you can do here is you can copy this, because it's the same equation for F2, right? For this, the other, friction factor. And you have to make sure that you got to change all these F1s to F2. And sometimes you miss one variable and you're screwed. So you shouldn't miss any variable. You know what variable I missed? Of course, you can't catch it because this is not live. I'm going to fix it now. So in your code, make sure this is Reynolds number 1, because Reynolds values are different. This is Reynolds number 2. Now it's okay. I was like, something is missing. Let's take a look at it one more time. F1, D1, Reynolds 1, F1. F2, D2, Reynolds 2, F2. Okay, -2 looks good. All right. Save it before you lose your code. Two equations are left, and that's the Reynolds number equation. Okay, Reynolds one is supposed to be rho times V1 times D1 over mu, and Reynolds 2 equals rho times V2 times D2 over mu, like this. Okay, look at this. That is good, 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 good. Now, do we have enough equations on those? We got to check it here. Let's check it. Looks like we have 26 equations, 26 variables. We should be able to solve this problem. However, if I actually run this code, this is not going to solve it. Why? Because there is a big problem here. You do have, not a big problem, it's just a problem. You have square root of f on this side, and then you have square root of f on this side in a logarithm. Also, you have Reynolds in a logarithm. Reynolds can't be negative. Square root of f, first of all, f can never be negative. That's the case. So we have to somehow make sure that EES doesn't iterate in the negative area. It does not iterate in the negative area, or it's going to be bad. That's not going to help us. So there are two ways to deal with this. If I run it right now, let's just run it to get the error message. So we got the error message. That's the error message. One or more equations constraint could not be solved. A specific tolerance, whatever, changing the guess values, blah, 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 blah. Yeah, so would you like to see more information? No, I know what's going on. But you can say yes and see what EES just gives you some stuff. But I know where the problem is. The problem is in these two Kohlberg equations, because you have Reynolds inside the logarithm. When it starts iterating for Reynolds, it might actually iterate in negative area, or for f the same idea. F can't be negative because you have square root there. There are two ways to deal with this. There is one traditional way and there is one super clever way to deal with this. I'm going to show you both. There's one way that you can go to options like this, and you go to variable input. That's like the traditional way. And then you can say, hey, EES, do this for me. For F1 and F2 that you can see here, I'm not sure if you can see the window. Let me see if you are. I guess you can actually see the window right now. Yeah, you should be good. So you ask EES that, hey, dude, look at F1 and F2, these two values. EES is iterating from infinity to positive infinity. That's not good. You can set a positive value, not zero. Zero is not acceptable. You can say like 0.0001 as like the lower, and like 10, I don't know, whatever, as the upper limit for it. And then give it a reasonable guess values. That's one thing you can do. And you have to do the same thing probably for Reynolds number, because Reynolds is also inside Kohlberg equation, and it shouldn't be negative ever. So that's going to affect your equation. So you got to do the same thing for Reynolds and for friction factor. I'm not going to do it right now because I'm going to show you a more clever technique. That is a technique that can help you in other problems, heat transfer problems, thermodynamics problems, anything that needs iteration, but it involves something, it needs something, and that's your engineering intuition. Engineering intuition comes from solving a lot of problems before. If you have solved a lot of turbulent problems before for internal flow, the range for the friction factor, in fact, for turbulent flow it's like between 0.01 to 0.02, 0.03, 0.04. That's maximum. You never get friction factor 10 or 11 or 15 in turbulent flow. In laminar flow, you can get a value like that, but never in turbulent flow. That's crazy. That never happens, right? So you use your intuition. How? One more time, I'm going to show you that intuition I'm talking about, because I'm going to share the Moody chart for you one more time. Let's take a look at Moody chart. So this is Moody chart again. And if you look at the value of friction factor, you can see that friction factor here, basically for turbulent flow, it's changing between 0.01 to 0.1. That's like the maximum. That's the range that we talked about. And if you have solved a lot of turbulent flow, fluid mechanics problems for this range of diameter, intuitively as an engineer, the number that we're talking about is probably between 0.01 to 0.04. It's not going to be anything bigger than that, or maybe 0.05. That I've never seen 0.05, to be honest with you. But for commercial steel, probably between 0.01 to 0.03 max or 0.04 max. So what am I going to do? Let's go back to EES, and I show you the clever technique first, and then I'll show you the traditional technique. So I'm going to show you two different techniques here. So this is EES again. We are back in EES, and in EES, I'm going to show you that clever technique. The clever technique is, hey, I know what the, generally what the value for F1 and F2 could possibly be. So I'm going to comment out these two equations like this. Now they're not part of the problem. However, I will give it a value. Then you might be like, what happened to Reynolds number? By using this method, you are getting rid of 2 of those 11 equations. And instead, you are adding by hand, you are given a value. Let's say F1 is 0.02 and F2 is 0.03, something like that. You might be like, hey, dude, these values we don't even know if these values are correct, by the way. I'm like, these are in the range. I know if they're not correct. But what is that going to do? This will force EES to come up with a solution. And also in this process, it disengages the Reynolds numbers that were inside the logarithm. So it will calculate some sort of Reynolds number, something, right? Once it comes up with the answer, that answer is like the closest after this iteration to the real solution. And then we're going to keep those solutions as the guess values for our actual solution. Look at this. So I gave it some values that I know are in the range. I force EES to solve the problem. Let's solve the problem. Oh, it is actually solving the problem. Let's see what it's get. It got some values here. All right, there are some unit problems. I'm going to take care of unit problems first. This head pump and whatever is supposed to be in terms of meters. These are not correct, by the way. And these m dot values are supposed to be like kilograms per second, something like that. So I'm getting rid of the potential unit problems eventually. And F1, F2 don't have any units. V1 and V2 have the unit of meters per second. Now I don't have any unit problems. Eventually, I'm looking for these two guys. Keep these guys in mind. You can pause the video, write them down. You're going to see something really interesting. 3 point something 8 and V2 is 4.3, right? And for the value and this value for Reynolds is like 350,000. This one is 151,000, something like that. These are not the correct values, but and total m dot is 26 kilograms per second. But EES iterated and converged to an answer, a realistic answer, because I gave it two realistic values for friction factor without even changing the range for variables, which I should have, but I didn't. But I forced EES to come up with a realistic answer. Now, this is the trick, the clever trick. Now that I have all these numbers, now I know where the actual Reynolds number could be, like around 150,000, 160,000, who knows, right? But I'm going to do this technique. Look at this button, G, update guesses. When you push this button in EES, it says this command will set the guess values of all the variables, the most recent calculated values. Continue, yes. So I'm going to get all the new guess variables. Look at this. If I go to calculate and if I go to options and variable info, these are the very realistic guess values for the head loss, for the pump head, for friction factor, not for diameter, for Reynolds number. For a lot of these guys, I have some solid values for guess values, which are very close to the real thing. Because EES is going to start iterating in that range, now I'm going back and I'm going to comment out these two fake friction factors that I added, and I'm going to uncomment the actual equations. Now I'm going to run it with solid guess values. Let's see what we get. Look at this, no error message. I did not even mess with the range of the variables. And I am getting the actual value. If you go back and look at those numbers, these numbers are still pretty close to the numbers you wrote down. But let's see what is the actual value of friction factor. I predicted 0.02 and 0.03. I got 0.018 and 0.022. And the value of total m dot that the first solution, the fake solution got us was 26. This is 29. That is close. I could have never known this. But how did this happen? How did this come, how is this possible? Because I have solved other fluid mechanics problems and I know the range of friction factor. And I just gave two fake friction factors which are in the correct range. And because of that, I forced EES to come up with solid, beautiful guess values. And based on those, I solved the actual problem. I did not even change the range of variables. I can save my code and I'm good to go. I don't even do anything else. However, let's say you didn't do this. Let's say you did not do this. You didn't know about this technique. And this is like you are just learning about fluid mechanics. You don't know like the fluid, the friction factor is not going to be 10 or 11. You just want the code to solve it for you. Okay, so what do? In that case, you go to option. You go to options and you go to variable info, and you have to go to the key factors here, which is friction factor, F1 and F2, and Reynolds number. These two guys, all the guys that might cause problems here for us. So let me just maximize this if I can. So I guess it's already maximized anyways. All right, sure, I guess that's all right. Where's Reynolds? So I have Reynolds number, two of these Reynolds numbers here, Reynolds number 1 and Reynolds number 2. I can restrict Reynolds to 0.001 to infinity, and this Reynolds to 0.001, whatever, to infinity. I can even say 2 million or whatever based on. And for friction factor, I can keep these as the guess values. And then you see the guess values are still the same guess values for the previous fixed solution. And then here I can say 0.001 to, let's say, I don't know, 10 or 2 or 5, because, it's 5 or something. It can't be 0. It can't do 0. And then you apply this, and then you can run it, and then you're going to get the solution. That's the case that you did not do that method that I did. They came up with the solid guess values and everything. Now the problem is solved, and if you want, you can actually take a look at, how beautiful the solution looks, and it looks like this, and you have all the values. They're nice. So this is how you solve a problem by iteration in EES, and a problem that normally you can't solve by hand. So there were a couple of techniques also that I showed you. And this was example 8-8 from Cengel's Fluid Mechanics book, 4th edition. And it's something that you have to solve numerically. Well, again, thank you very much. Again, make sure you subscribe to this channel, because I try to upload 1 video a day in this area. Sometimes it's EES, sometimes heat transfer, fluid mechanics. And so I try to solve problems or cover some of the concepts that in fluid mechanics or heat transfer thermodynamics, the students are, or even engineers who graduated, and they're kind of struggling with some of really, interesting key concepts. Thank you very much, and you guys have a good day.